Hmm. Okay, so I'll just start discussion on week 4 lectures and some problems associated with it. Good evening and welcome to this session. I'm Shreya. Before proceeding, do you have any questions? Please feel free to ask pertaining to group 4, 3, anything.
Good evening, ma'am.
Yes,
Can,
yes,
can
sir.
you explain, ma'am? This one, two sample test of the book.
Yeah, I'll do it. I'll explain with an example. Okay?
Yes, ma'am.
Okay.
Okay, ma'am.
Okay, so if not anything else, I'll just start with the session. So, briefly, I'll touch up on what was discussed. So, these concepts were discussed: Pearson's goodness of fit test, degrees of association between qualitative and quantitative variables. These were also discussed. So for qualitative tests, there was this chi-square test of independence to test the relationship or degrees of association, or tests by odds ratio, some measures of odds ratio. And also for quantitative variables, we learnt about the correlation coefficient and the coefficient of determination that would give us some idea on the degrees of association between two variables. Degrees of association between two variables. And also two sample tests for mean and for variance for population proportions were discussed. Tests for mean was there were two categories. One was when the samples were independent, then we had a two sample t test, and there was another form of test for mean where the samples were paired, like observations pertaining to a single individual with some before after criteria. This is the unit on which observations were taken, and some before after or pre post, some sort of criteria where the samples in uh, group 1 were paired to samples with group 2. So those sorts of tests were also discussed. So with this, I will just move on to some examples which will help you understand how to solve these problems. Okay, so I'll just start. Let's say we have this question. So it is given that a printing press runs some sort of pilot analysis and finds that the number of defects, there are a few defects in printing mistake, and the press runs the analysis for approximately 60 books and gets this distribution: observed number of defects in 31 books, 14 books. So there are 0 defects in 31 books out of these 60 books, 1 defect in 14 books out of these 60, 2 in 8 out of these 60, and 3 defects in 7 books. So the question is, can the press assume that the distribution of defects is a Poisson distribution? So how do you think we should go about this problem? What should be the starting point? And what sort of a test is this? Anyone? Okay, so what we are trying to do is we are trying to fit a Poisson distribution and determine how good that Poisson distribution is. So this is a sort of goodness of fit test for fitting a Poisson distribution. Okay, so if you remember, if x follows a Poisson distribution, what was the parameter of that distribution? How many parameters were there? Okay, so the Poisson distribution is characterized by one parameter, which is the lambda, and this one, expectation of x is lambda, variance of x is also lambda. This is a characteristic of a Poisson distribution. This we already know. So now if we have to fit a Poisson distribution to this data set, then we need to know, so in order to fit a Poisson, we need to know lambda. So from here we know that expectation of x, if x follows Poisson, is lambda. So in other words, we can estimate lambda by sample mean. So if we consider this table, this is my xi, this is my fi. X is the number of defects and fi is the frequency. So sample mean will be summation xi fi by summation fi. So this will be 0 into 31 plus 1 into 14 plus 2 into 8 plus 3 into 7 by 31 plus 14 plus 8 plus 7. So this will be equal to 14 plus 16 plus 21 divided by 60. How much do you get this? Yes, 0.85. Okay, so now we know we have an estimate of lambda and we can fit a Poisson distribution. So up next we'll do that. We'll fit a Poisson distribution. So here we had number of defects. Here we had the observed frequency. So this was 0, 31, 1, 14, 2, 8, 3, 7. This was the original table. We'll do one small modification here. We'll write 3 or more. Because if we see here, from the existing sample for 4, 5, 6, all the frequencies were 0. So we'll tweak the table in such a way, we'll write it like this, 3 or more. And then we'll fit a probability x equal to x, where x will follow Poisson 0.85. Okay, so here if we remember, the PMF of a Poisson distribution was e to the power minus lambda to the power x by x factorial. So we'll put it here. So for this one, for x equal to 0, we'll put e to the power minus 0.85 into 0.85 to the power 0 divided by 0 factorial. This one we'll put e to the power minus 0.85 to the power 1 by 1 factorial. For x equal to 2, we'll put e to the power minus 0.85 into 0.85 square by 2 factorial. And for this case, we'll find out the probability. So here, probability x equal to 3 or more, that is probability x greater than equal to 3. This one can be written as 1 minus probability x equal to 0 plus probability x equal to 1 plus probability x equal to 2. Do you agree? Because we are taking 3 onwards. So total probability should be 1. So greater than equal to 3 will be 1 minus probability x equal to 0 plus x equal to 1 plus x equal to 2. So for the last one, we'll write it as, let's say this is P0, P1 and P2. We'll write it as 1 minus P0 minus P1 minus P2. So what are the values? What are you getting here? Please calculate and let me know. P0 is
it 0.36 something?
should be somewhere around 0.42. Can you please check once again? This will be e to the power minus 0.85. This should be e to the power minus 0.85 into 0.85. This should be minus e to the power 0.85 into 0.85 whole square by 2. Can you please do it now? This is coming out as 0.427.
Yes, ma'am. Yes.
This will be 0.363. This is somewhere 0.154. Are you getting this? So then this will be 1 minus adding these three, 0.427 plus 0.363 plus 0.154. This will be 1 minus 0.944.
Zero 0.056.
This will be 0.056. So now we have a revised table. So number of defects, this one was 0, 1, 2, 3 or more. Observed values were 31, 14, 8, 7. Expected values or probabilities were 0.427, 0.363, 0. What was the number here? 154, and this was 0.056. So the expected frequencies will be, we'll multiply the probabilities with the total number. The total number was, this one was the observed total, 60. So this will be 0.427 into 60, 0.363 into 60, 0.154 into 60, 0.056 into 60. So how much do we get? The expected frequencies. This will get as 25.62. This will be 21.78. This will be 9.06. And finally, this will be 3.18. So now we have our observed frequencies and the expected frequencies if we assume that the defects distribution is following a Poisson distribution. So now our goodness of fit test statistic is, it's a chi-square, which is summation observed frequency minus expected frequency whole square for ith group by expected frequency for ith group. I equal to 1 to here 1 0 1 2 3 4. So if we try to find out how much are we getting this chi-square value, this will be 31 minus 25.62 whole square by 25.62 plus 14 minus 21.78 whole square by 21.78 plus 8 minus 9.06 whole square by 9.06 plus 7 minus 3.18 whole square by 3.18. How much are we getting this? So this entire thing, the value should be somewhere around 8.089. Did anyone get this? Okay, so the calculation is such that chi-square value comes around to be 8.089. So now our H0 was x follows Poisson, and H1 was x does not follow Poisson. So this is the test statistic, the observed value. So the decision rule will be, we'll reject H0 if and only if observed chi-square is greater than chi-square with some degrees of freedom 0.05. So what will be the degree of freedom? It will be number of categories minus 1 minus number of parameters estimated. So here we fitted Poisson and we got estimate of lambda. So 1 parameter estimated. So the degrees of freedom would be, we had 1, 2, 3, 4 categories. So this will be 4 minus 1 minus 1, that is 2. So this will be nothing but chi-square 2 0.05, that is the upper alpha 0.05 point. What is it essentially means is that if this is my chi-square, then this point, let's say this is a chi-square with df2, then this area, the area above this point will be 0.05. So from the table we find out, so let's say this is the chi-square table. I'll just copy it 1 second. So from here we have to find out chi-square 0.05 and degrees of freedom is 2. So this will be our upper alpha point. So this point is 5.991. This is 5.991. So in our case, observed chi-square was 8.089, which is greater than 5.991. This point is 5.991, which is the chi-square 2 0.05. Thus we are going to reject null and conclude that the distribution is not Poisson. Is it clear? Any doubt in this question?
No.
Okay. So I'll just proceed to the next one. So a food services manager for a baseball park wants to know if there is a relationship between gender and preferred condiment on a hot dog. So these are the number of condiments, number of categories. There are 3, and gender categories there are 2. So we have to test the hypothesis if there is a relationship between gender and preferred condiment or not. So the H naught, the null hypothesis, is that no relationship. That is, gender and preferred condiment are independent. And my alternative is that there exists a relationship. So this is the test of independence. So how are we going to do it? We have the row totals and the column totals here. So under H naught, if actually these two were independent, then we would have the expected numbers as this. So this is gender, this is male, female. So this is ketchup, this is mustard, this is relish. Okay. So the expected numbers would be, for this one, for this cell, 40 into 48 divided by 100. Why so? Because probability x equal to a, y equal to b, if x and y are independent, then this is probability x equal to a into probability y equal to b. So this, let's say if this is some small x by 100, because the total is 100, then this will be probability x equal to a, that is 40 by 100 into probability y equal to b. So let's say this is a and this is y. b1, b2, a1. 48 by 100. So then this number would be 40 into 48 by 100. Is it clear why we are doing this? So similarly, we'll try and get the expected value under H naught. So for mustard, it will be 42 into 48 by 100. For this one, it will be this will be 48 into 18 by 100. Similarly, this one would be 40 into 52 by 100. For this one, it will be 42 into 52 by 100. And this one will be 18 into 52 by 100. So finally, what would the counts look like? So ultimately, we would have so this one would be 19.2, 20.16, 8.64, 20.8, 21.84 and 9.36. So now we have the observed counts and the expected counts. So then now we have to find out the test statistic. So the test statistic is similar which is summation observed minus expected whole square by expected. So this will be 15 minus 19.2 whole square by 19.2 plus 23 minus 20.16 whole square by 20.16 plus 10 minus 8.64 whole square by 8.64 plus 25 minus 20.8 whole square by 20.8 plus 19 minus 21.84 whole square by 21.84 plus 8 minus 9.36 whole square by 9.36. How much do you get this? So this one, any of you calculated? So if you calculate, you'll get it to be somewhere around 2.95. So the rejection rule here is we'll reject H naught if and only if chi-square observed is greater than chi-square df 0.05, because we have been asked, to test at a significance level of 10%. So this one will be 0.1, where df is what? Number of row categories minus 1 into number of column categories minus 1. So here we have 2 minus 1 into 3 minus 1, that is 2. So we have to find out chi-square to 0.1. So let us check. Chi-square to 0.1, that is 4.605. So chi-square to 0.1 is 4.605. So our thing is less than 4.605. So the conclusion is we do not reject H naught and conclude that there is no relationship, because H naught said that there is no relationship, and we conclude that there is no relationship between gender and condiment preference. Is it okay? Shall I move on to the next one?
Yes, ma'am.
Okay. So question 3 says a scientist wants to find if mean weight of two species of turtles differ. From past studies, he assumes that variances of weights in species A and B are such and such, collects data on 400 turtles on species A, 350 turtles of species B, calculates their average weights. So we have two samples here. Species A is one sample and species B is the other sample. So here he let's say this is NA. The number of samples he has collected information is 400. Here it is 350. XA bar, if let's say X is the weight of a randomly selected turtle, this is my variable, then XA bar is calculated as 40 kg, XB bar is calculated as 42 kgs. And from previous studies, it is assumed that the variance of weights of species A and species B are 18.5 and 16.7. So, sigma A square was 18.5, which is known, and sigma B square is 16.7, which is also known from beforehand based on some population data. So here in the test statistic is, let's say this is the mean weight of species A and this is the mean weight of species B. So then our H0 is versus H1 not equal to mu B. This is a two sample test. Now how will I know, will it be a T test or a Z test? Because sigmas are known, we will conduct a 2 sample Z test. So then the test statistic would be XA bar minus XB bar minus mu A minus mu B divided by root over sigma A square by NA plus sigma B square by NB. Because we are assuming that species A and species B are independent. So this one under H0 follows normal 0 1 because this is 0. So the test statistic we'll find out as XA bar minus XB bar. Under H0 this becomes 0 by root over sigma A square by NA plus sigma B square by NB. So this will be 40 minus 42 divided by 18.5 by 400 plus 16.7 by 35. So this will be something around minus 2.06. So now our decision rule will be based on H1. So H1 was mu1 not equal to mu A not equal to mu B. So decision rule is we'll reject H0 if and only if, or we'll like it this way, if Z less than minus Z alpha by 2 or Z greater than Z alpha by 2, where Z is a standard normal distribution. If it falls here or in this range such that the total area is 0 is alpha, then only we are going to reject. Or in other words, we will reject H0 if and only if Z less than minus Z 0.025 or Z greater than Z 0.025. Here nothing has been said, So we'll take 5% level of significance, alpha equal to 5%. So then this point, if alpha by 2, where alpha is 5%, 0.025 is nothing but 1.96 plus minus 1.96. So here our test statistic value is minus 2.06. So this is less than minus 1.96. Hence, we reject H naught and conclude that mean weight of the two species differ. Okay. This same thing, in one sentence it can be written as reject H naught if and only if mod Z is greater than Z alpha by 2. So since our value is less than 1.96, or in other words, if we take modulus, then 2.06 is greater than 1.96. Thus, we are rejecting H naught and concluding that the two mean weights of the two species differ. Is it okay? Shall I move on to the next one? Hello, am I audible?
Yes, ma'am.
Okay. So, now we have this one. So, to compare the performance of two call centers in terms of average call lengths, 20 calls from each call center are randomly selected and the average call lengths are calculated. So, find out if the difference is statistically significant or the difference is a chance occurrence. So, we have to compare performance in terms of average call lengths. So, our H naught is the average call lengths are same versus the alternate average call lengths are different. So, now we have to find out if this difference is statistically significant or it is a chance occurrence. So, this one, call center A, this is based on, the calculation is based on 20 samples, or in other words, NA is 20, and this is the sample standard deviation, which is based on 20 samples. So here we are going to apply a 2 sample t test, because the population sigma A square, sigma B square are unknown. Is it okay? So instead of sigma A square and
Yes, ma'am.
sigma B square, we are going to use the sample counterparts for this thing. And also there is another underlying assumption that sigma A square and sigma B square are different. They are not same. If this is a related concept not really explained in the lectures, but if we assume these the two variances to be equal, then we take some sort of a pooled estimate and then proceed with our test. This is another implicit assumption that we have taken here, that sigma A square and sigma B square are different, and these true variances are unknown. Okay, so with that, then our test statistic is XA bar minus XB bar minus mu A minus mu B divided by root over SA square by NA plus SB square by NB, which under H0 follows a T distribution with N1 plus N2 minus 2 degrees of freedom. Okay, so the rejection rule will be, we'll reject H0 what happened? We'll reject H0 if and only if the test statistic value is greater than, or modulus of test statistic value is greater than T N1 plus N2 minus 2 alpha. Or if we follow a p-value method, then we'll reject if probability of a T distribution N1 plus N2 minus 2 greater than the observed test statistic is less than 0.05. Okay, so here we'll just compute the value. So under H0, then what will be our the value of the test statistic? So our test statistic value is XA bar minus XB bar by root over SA square by NA plus SB square by NB. So what is this? X1 is 122 minus XB is 135 divided by root over SA square is how much? 20 into 20 divided by 20. NA was 20 and this is 15 into 15 by 20. So the value is 2.3256. So here we'll use this one. This is better. So here the degrees of freedom was N1 plus N2 minus 2 is T 40 minus 2, that is T 38. So observed value was 2.3256 and T 38 0.025. This value comes out to be 2.0244. This you can calculate from the tables, also from softwares. I have calculated this from R. Okay. So we'll here this value, observed value, is greater than the critical point and hence we reject H0 and conclude that there exists difference in performance between the two call centers. Is it okay? If we wanted to use a p-value approach, then we had to calculate probability mod t greater than our t observed. If this is less than alpha, that is 0.05, then we would have rejected h naught. But I think this is easier, this one. Okay, shall I proceed to the next one? Any doubt here?
No, ma'am.
Okay, so this is the next question. Here we have some pre-post kind of a thing. So this is most likely to be a paired t-test. Still, we'll just read. A sample of n students were given a diagnostic test before studying a particular module, and then again after completing the module we want to find out if in general the teaching leads to improvements in students' knowledge or skills. So h naught, let's say this is 1 denotes pre-module, 2 denotes post-module. So here n we have, how many paired samples do we have? We have 1 to 20. N is 20. So the h naught null hypothesis is mu1 equal to mu2. But the alternate is, in general our teaching leads to improvements. We want to see if there is any improvement or not. So the hypothesis is mu2 greater than mu1. If this is true, then we can say that the module is improving the scores. Correct. Now, in order to conduct a paired t-test, why is it a paired t-test? Because these observations are based on the same sample, not from two different samples. Okay. So, in order to do this, what we have to find out? So, the first and foremost thing is to find out D, which is post-module minus pre-module. So, here I have already kept it calculated. This difference is nothing but D. So, D is post minus pre. If we take this one for example, this is 29 minus 24. So, we get a value of D. Then, we have to find out D bar, which is summation di by n. So, if we find out, if we add all of these, the total would be so if we sum up di, what will the total be? This would come out to be 41. Okay. So then D bar is 41 divided by 20, which is 2.05. So as we know in our test statistic, the formula is D bar minus under h naught it will be 0 by root over st by n. So st will be summation di minus d bar whole square by n minus 1. So here in this column what I have given is summation di minus d bar sorry, not summation. This column shows di minus d bar whole square. So let us just check if whatever I am saying is true or not. D bar is 2.05. So if we take this one, let's say the last one. Okay, this one. Or let's say this one. This is the easiest one. So for this one, d is 0, d bar is 2.05. So then d minus d bar whole square is 2.05 whole square, which is 4.2025. Okay, so we have validated. This column is di minus d bar whole square. This one is summation. So next we'll do summation di minus d bar square. This is 152.95. And SD is 152.95 divided by 20 minus 1, that is 152.95 by 19. We are getting it to be 8.05. This figure. Okay, so based on these calculations, now we have d bar as 2.05, ST as 150, what was that? 152.95 by 19, that is 8.05. So then the test statistic is d bar by root over SD by N. So this will be 2.05 divided by 8.05 by 20. So how much do we get this as? Oh, sorry, 1 second. I made a mistake. So this will be this is SD. So the test statistic is SD by root n. This is not variance, no, this is, so this is the test statistic. D bar by SD by root n. This is 2.05 by 8.05 divided by root over 20. So how much do we get this as? This will be something around, some mistake I am making, it seems. 1 second. Oh, understood. This one SD will be root over this thing. This is 2.83. So this one will be 2.83. and the final answer will be 3.231. This comes out to be not 3 point something. This is 2 point something. 2.05 divided by 2.83 into root 20. Yes. Okay. This is 3.239. Okay. So our rule is we'll reject H naught if and only if the observed T, so the alternate was mu2 is greater than mu1. So observed T is, so this is based on x2 minus x1, if you remember D, the calculation of D, post minus pre, x2 minus x1. And the similar sign we have in alternate, that is mu2 minus mu1 will be greater than 0. That is the alternate thing. So the null rejection rule will be reject H naught if and only if T observed is greater than T some df 0.05, where df will be n minus 1, that is 19. So from the table we find that T19 0.05 is 1.729. So since our T observed is greater than 1.729, thus the conclusion is we reject H naught and conclude that the module improves performance. Is it okay? I'll just repeat the entire thing so that it's clearer. So what we are doing, the first thing is to formulate what will be the null or the alternate hypothesis. So null is there is no improvement. Whatever was pre, same thing remains after post. H1 is the scores improve or mu2 minus mu1 greater than 0. This is mu2 minus mu1 equal to 0. So D is nothing but x2 minus x1. So we are calculating this D values, getting D bar as summation di by n, getting ST as square root of summation di minus D bar whole square by n minus 1, taking the differences, squaring it up, adding it up, dividing it by 19, taking the square root, and then we are getting ST. and the test statistic is d bar by st by root over n. And if the rule is, if t observed is greater than t n minus 1 0 alpha, then we are rejecting H naught. This is what we have done. So first we have calculated D, that is post minus pre. Then we have calculated di minus d bar whole square in these columns. Then we have added it up, divided it by 19. So whatever here we have written, I'll just write it properly. This is SD square 8.05. How we are getting it? 152.95 divided by 19. This is 8.05. And so SD square is this one. So SD is root over 8.05, which is 2.837. So the same thing, we have taken it here, calculated SD 2.837, calculated the observed statistic, which came out to be 3.239, which is greater than the tabulated t value at 5% level of significance and 19 df n minus 1. And so we are rejecting H naught and concluding that module is improving performance. Is it clear now?
Clear, ma'am.
Okay. So we'll proceed to the next one. So this magazine reported the result of a telephone poll of 800 adult Americans. The question posed was, should federal tax on cigarettes be raised to pay for healthcare reform? These were the responses of non-smokers and these were the responses of smokers. So they've asked, is there sufficient evidence at alpha equal to 0.05 to say and conclude that two populations differ significantly with respect to their opinions? So here it is a test for population proportions. So if let's say this is P0 351 by 605 and P1 hat rather 41 by 195, we are interested to find out if P0 equal to P1 versus H1, P0 not equal to P1. So P1 hat or estimate is 351 by 605. This is 0.58. P1 hat is 41 by 195, that is 0.21. So for testing of proportions, the test statistic is P1 hat minus P2 hat minus 0, because under H naught it becomes 0, to root over P hat into 1 minus P hat 1 by N1 plus 1 by N2. So now we have to find out P hat or the pooled estimate. So pooled estimate P hat, total people who have responded in yes, that is given as n1 into p1 plus n2 into p2 hat by n1 plus n2. So then we have p hat as 605, or we have the absolute numbers. So how many responded yes? 351 plus, here how many responded? 41 divided by 605 plus 195. So the pooled estimate, it will come out as 392 by 800, that is 0.49. So then, since the sample size is large, n is 800, we can approximate this by a normal thing, and the test statistic will be p1 hat minus p0 hat by p1 hat by root over p hat into 1 minus p hat 1 by n1 plus 1 by n0 plus 1 by n1. So this will be 0.58 minus 0.21 divided by root over 0.49 into 1 minus 0.49 to 1 by 195 plus 1 by 605. So this value will come out as something like 8.99. And since the sample size is large, we'll assume that this follows a normal 0,1 under H0 approximately asymptotically. So the rejection rule is, we'll reject H0 if and only if Z is greater than Z alpha by 2, because the alternative hypothesis is that they are not equal. So here alpha is 0.05, so then this value is nothing but 1.96. So here, since this one is greater than 1.96, therefore our answer is, we'll reject H0. And what will we conclude? That they differ. Smokers and non-smokers differ in opinion. Is it okay? Shall I move on to the next one?
Yes, ma'am.
Okay. Okay. So this question says that an automatic machine was designed to pack exactly 2 kg of vanaspati. A sample of 100 tins was examined to test the machine's performance. The average weight was found to be 1.96 with a standard deviation of 0.1 kg. Is the machine working properly at 1% level of significance? So firstly, we'll see, let's say that if the machine is working fine, then it should pack exactly 2 kg of vanaspati. It is designed to pack, so mu will be equal to 2 versus H1, mu is not equal to 2. So since this is a test for mean, so this sample size is large, so we can assume that this follows a normal distribution. Yes, so the test statistic is x bar minus mu by sigma by root 10. So we can assume here the test statistic will be x bar minus 2 by sigma by root 10 that would follow a standard normal distribution since the sample size is large. So here what we have is that instead of sigma we have been given the standard deviation. So standard deviation of x is given as 0.01. So instead of sigma we'll put this one here and this will be our divided by root over 100. So x bar minus 2 by 0.01. This is the test statistic. So we have here 1.94 minus 2 by 0.01. So this is minus 6. So what we are doing here is reject H naught if and only if Z observed is greater than Z alpha by 2 or 1.96. So our Z observed, that is x bar minus mu under H naught, x bar minus 2 by 0.01 is minus 6. So modulus of Z observed is 6, which is greater than 1.96. So hence we reject H naught and conclude that mu not equal to 2. So in other words, the machine is not functioning properly. Is it okay? Any doubt?
Please show the previous slide. Okay, ma'am, thank you.
Okay. So now I'll proceed to the next one. So here they are saying in a sample of 8 observation, sum of squared deviations of items from mean was 94.5. In another sample of 10 observations, value was found to be 101.7. Test whether the difference is significant at 5% level. Here what we are testing difference of is, this is test for actually variances, if you see, because we are taking sum of squared deviation from mean. So this is nothing but n into variance, right? So okay, in a sample they are saying, so this one is nothing but from the mean. So what they have calculated is summation x by minus x bar square, which is nothing but n minus 1 s square. Okay, these they have calculated. So the H naught is that sigma 1 square from the sample of 8 observations equal to sigma 2 square versus sigma 1 square is greater than sigma 2 square. So here the test statistic would be S1 square by S2 square, which is nothing but 1 by n1 minus 1 into summation xi minus x bar whole square by 1 by n2 minus 1 summation this one will be xi1 minus x1 bar x2I minus x2 bar. So these things they have calculated. So this will be 94.5 by 8 minus 1 by 101.7 divided by 10 minus 1. So this one we'll get as 13 point, sorry, this one we'll get as 94.5 divided by 7 is 13.5 by 101.7 divided by 9, 11.3. 13.5 divided by 11.3 is something around 1.195. Okay, and the rejection rule is we'll reject H naught if and only if the test statistic is greater than, this is a ratio of two standard deviations, so it will be an F statistic with numerator n1 minus 1, n2 minus 1 df and 0.05. So let's say if this is this statistic with n1 and n1 minus 1 or n2 minus 1 degrees of freedom, this is the point above which 0.05% is the area. So from the table we try to find out, so our n1 minus 1 is 8 minus 1, that is 7, and n2 minus 1 in the denominator is 10 minus 1, that is 9. So across nodes rows we'll find out df minus 1. So here we have 7, and for this one n2 minus 1 we have 9. So and this is the value for alpha equal to 0.05. So the cutoff value is 3.29. So the cutoff value is 3.29. Our statistic value is S1 square by S2 square. It came out as 1.195, which is less than 3.29. Hence, we do not reject H naught and conclude. What was the conclusion? No significant difference between two samples. There is no significant difference between two samples. Is it clear?
Yes, ma'am.
Okay. So let us work on this one. Weights in kg of 10 students are given as below. based on the given information, can we say that variance of distribution of weights of all students is equal to 20? Your conclusion should be based on 5% confidence interval. Okay. So here the null hypothesis is that sigma square equal to 20 versus the null alternate hypothesis is that sigma square is not equal to 20. So these are the weights of 10 students in kgs. So the average, let x denote weight of a student. So then observed x bar is 38 plus 40 plus 45 plus 53 plus 47 plus 43 plus 55 plus 48 plus 52 plus 49 divided by 10. This one is how much? X bar is 47. Now, can we say that variance of distribution of weights is equal to 20? So, in order to test for variance, the test statistic is given by n minus 1 sigma s square by sigma square or sigma under h naught square, which follows a chi-square n minus 1 under h naught. Okay, sorry. So this is the n minus 1 into s square, where s square is the sample standard deviation, by sigma square. This follows chi-square n minus 1. This is an already established thing. So we are going to take this into account and formulate our hypothesis. So s square is nothing but, this is 1 by n minus 1 summation xi minus x bar square. Okay, so we have to find out n minus 1 s square. So this will be summation xi minus x bar whole square. So here from this table we are going to find out this quantity, the upper quantity. And our test statistic will be summation xi minus x bar whole square divided by 20. And the rejection rule will be, we'll reject h naught if and only if t observed is greater than chi-square n minus 1 0.05. Okay, because this holds true always, under h naught sigma square will be replaced by whatever is sigma square is under 20. So then that would also follow a chi-square n minus 1, and if it is more extreme than this cutoff, then we are going to reject h naught. So the task remains to find out summation xi minus x bar. So here we have 10 observations, 38, 40, 45, 53, 47, 43, 55, this is 48, 52, 49, 48, 52, 49. So 38 minus 47, 40 minus 47, all these things will compute. Then we'll square it up, and sum of these squares would give us summation xi minus x bar whole square. So finally this would come out as something around 280 if you do the calculation. We can do it also. Let's see it come out. So what we are going to have here, we have 11 square, 9 square, sorry, 9 square plus 7 square plus 2 square plus 6 square plus 4 square plus 8 square plus 5 square plus 2 square. How much do we get this?
299.
299. Are you sure? Or did I make a mistake? 81 plus 49 plus 4 plus 36, 16 plus 64 plus 25 plus 4, 279 I am getting.
29.
Okay, one I have missed here, plus 1 square. Yeah, 280. This one I missed. Okay, so this one comes out to be as 280. So finally what we are having, 280 by 20, that is 14. Now we'll find out chi-square 19, 0.05. So this one, chi-square 19 and 0.05 here. So this is 30.144. So this is 30.144, which is not which is way more than what we have. We have only 14. Thus, we do not reject H naught and conclude that this one, population variance is equal to 20. Population variance equal to 20. Okay. So the important thing to remember is that the test statistic would be summation, where it went. This is n minus 1 s square by sigma under h naught square. This is the test statistic, which follows chi-square n minus 1, and if it is beyond some point, then we are going to reject H naught. Okay, and if they are saying your conclusion should be based on 5% confidence interval, you can use this one also, or you can compute with the chi-square values the lower confidence interval, upper confidence interval, and if 20 belongs to that interval, then we'll do not reject H naught, otherwise we'll reject H naught. But I think this is far easier, this process. Okay, any doubt?
No.
Okay, so finally, now this question. Suppose a dice was thrown 60 times with the following results. Do you think that the dice is unbiased at 1% level of significance? So a dice is thrown 60 times with the following results. It means that if it is unbiased, then all sides would have equal probabilities, 1/6, 1/6, 1/6 and 1/6. So then the expected frequencies would be 10, 10, 10, 10, 10, 10. It should be equal if it is unbiased. So now we have the observed frequency and the expected frequency. So the chi-square statistic will calculate 10, 6 minus 10 whole square by 10 plus 10 minus 10 whole square by 10 plus 8 minus 10 whole square by 10 plus 13 minus 10 whole square by 10 plus 11 minus 10 whole square by 10 plus 12 minus 10 whole square by 10. So this will come out as 1 by 10 into 4 square plus 2 square plus 3 square plus 1 square plus 2 square. That is 1/10 of 16 plus 4 plus 9 plus 1 plus 4. That is 3.4. And we'll take chi-square. How many categories are here? 1, 2, 3, 4, 5, 6. So the degrees of freedom will be 6 minus 1. So we'll find out chi-square 5, 0.05. Oh, at 1% level of significance they have said. So then we'll calculate 0.01. So chi-square 0.01 will be this column, and 5 degrees of freedom, that is 15.086. So this is 15.086, and the rule is we'll reject H naught if and only if observed chi-square is greater than chi-square 5, 0.01. But here it is less than 0.01, so H naught was unbiased. So then we fail to reject H naught and conclude that yes, it is unbiased. Is it okay?
Okay, ma'am.
Okay. So now I'll proceed to this one. Now suppose we have a basketball coach who uses a new training program to see if it increases the number of players who are able to pass a certain skills test compared to an old training program. He recruits 50 players to each program, so this sum are 50. The following table shows the number of players who passed and failed the skills test based on the program they used. Calculate odds ratio and interpret, and formulate a 95% confidence interval for the odds ratio. Okay. So, from here, if we have to find out, first we have to find out the odds ratio. Now, odds ratio is a ratio of two odds. So, odds of passing for the new program is what? This is 34 pass by fail. So this is 34 by 16. This is how the odds are calculated. Odds of fail to pass, odds of failing, if I had to write, odds of failing for the new program would be just the reverse, 16 by 34. Here we are concentrating on the ability to pass. So we'll focus on odds of passing. Okay. So odds ratio that we are trying to find out is odds of passing for the new program divided by odds of passing the old program. So this is 34 by 16 by odds of passing the old program was 39 by 11. So this ratio comes out to be 0.599. This is the odds ratio. If we do not go for interpretation, naively also the odds ratio of passing will be 34 into 11, this into this, divided by 39 into 16. Same thing, okay? But it's better to formulate this way because then it gives us clarity and it shows us how we can interpret an odds ratio. Okay, so odds of passing the new program is 0.59 times the odds of passing the old program. So what it essentially means is that if we have to interpret, then we can write it like odds of passing the new program is equal to 0.59 times the odds of passing the old program. So if we have to say something about the efficacy of introduction of the new program, then in other words we can say the new program reduces odds of passing by 41% approximately. If the odds of passing was 1 in the old program, then now for the new program odds of passing is 0.59. So 0.41 into 100% reduction has happened. reduction in odds. This entire thing I have written like this. In other words, the new program reduces odds of passing by 41%. So is the new program effective? Zero 0.599, so this is 40.1. So then from here we can say that the new program is even more stricter. This is in terms of the interpretation, because here the coach wants to see that if it increases the number of players, but the possibility of increasing the passing rate is becoming low. Okay, am I clear? Is this part clear?
Ma'am, explain much more, ma'am, this part. Okay.
So here we have odds of, you understood how we are calculating the odds of passing?
Yes, ma'am.
Okay.
Yes, ma'am.
So the odds ratio is the odds of passing of the new program with respect to the old program. So this is the odds ratio is less than 1. So what it is implying is that the odds of passing the new program is less than odds of passing the old program. How much is it reducing? It is reducing point by 0.4011. Because it is, so let's say this is half, 0.5 only. To be just consider this to be 0.5. So whatever was the pass to fail ratio for the old program, that ratio is becoming half for the new program.
Okay, ma'am. Understood.
So then it is reducing the odds of passing by this percentage. So what is actually implying is that the new program is even more stricter, because it is reducing the passing odds. Odds means chances. Okay, so this is how
Okay,
you
ma'am.
should interpret an odds ratio. And finally they have asked, what they have asked? They have asked formulate a 95% confidence interval for the odds ratio. So 95% confidence interval. To find this out, first we have to find out the log of odds ratio. This is the first thing. So here log of 0.599. This is log with base e, okay, not with base 10. So this one is ln 0.599, that is minus 0.512. This one in the notes is mentioned as theta, and standard error of theta is given by 1 by n1 plus 1 by n2 plus 1 by n3 plus 1 by n4. So the 95% confidence interval for theta is given as theta plus, is given as theta minus 1.96. It is assumed, since the numbers are large, it is assumed that theta follows a it is approximately normally distributed. So this one which is theta naught minus 1.96, this is my theta naught, okay, root over 1 by n1 plus 1 by n2 plus 1 by n3 plus 1 by n4 theta naught plus 1.96 root over 1 by n1 plus 1 by n2 plus 1 by n3 plus 1 by n4. So then this will be ln 0.599 minus 1.96 into 1 by n1, n2, n3, n4 are these cell values. So 1 by 34 plus 1 by 39 plus 1 by 16 plus 1 by, how much was it? 11. And ln 0.599 plus 1.96 into this thing, 1 by 34 plus 1 by 39 plus 1 by 16 plus 1 by 11. Okay. So if we calculate this, how much are we getting in this as? So 95% CI for theta, which is log of odds ratio. This is minus 0.512 plus minus 1.96 root over this thing. Now we are going to calculate 1 divided by 34 plus 1 divided by 39 plus 1 divided by 16 plus 1 divided by 11. So this comes out to be 0.208. So this will be 0.208. So the confidence interval is minus 0.512 minus 1.96 into root 0.208 minus 0.512 plus 1.96 into root over 0.208. So this will be into 1.96 minus 0.512 into 0.4409 minus 0. Sorry, this one will be no, 1 second. So square root of 0.208, this is 0.456. sorry Okay, minus 1.96 into 0.45 minus 0.512 plus 1.96 into 0.45. Zero 0.882 0.512 plus 0.882. So this will be 1.394 to 0.37. So far we have just obtained 95% confidence interval for log odds ratio. So then this one, whatever we have obtained, minus 1.394, 0.37, this is the 95% confidence interval for log of odds ratio. So then 95% CI for odds ratio would be e to the power minus 1.394 and e to the power 0.37. So the final answer will be e to the power minus 1.394, that is 0.248 to e to the power 0.37, 1.448. So this will be the answer. Okay, so the main in a single word, if I have to summarize, then 95% confidence interval for odds ratio is given as e to the power log odds ratio minus 1.96 root over 1 by n1 plus 1 by n2 plus 1 by n3 plus 1 by n4. This is the lower limit, and the upper limit is e to the power log of odds ratio plus 1.96 root over 1 by n1 1 by n2 plus 1 by n3 plus 1 by n4. Is it okay? I hope this is clear.
Yes, ma'am, clear.
Okay, thank you. So then I'll just move on to the last question for today. Any questions, queries? Okay. Yes, Mr. Kamal. Say, you have a question? Your hand is raised. Hello? Okay, I think that's a mistake. Anyway, I'll proceed to the next one. So here we'll ask after completing last. Okay, fine. So here we have a test of hypothesis on husband's age and wife's age data, in which sample correlation based on n equal to 170 couples is 0.939 to test rho equal to 0 against alternative rho not equal to 0. So this is the test for correlation. So if nothing is given, then if a set of, let's say xi, this is husband's age, and let's say this is wife's age, for let's say n couples. If it is given, if this is the data set that we have, then we'll calculate sample correlation using this formula. Okay, we'll get the x bar for husband's age, y bar for wife's age, do these sorts of calculation, and then we'll arrive at r. So here, let's say from a data set they have computed r, and they want to find out if rho equal to 0 against rho not equal to 0. It implies that if rho equal to 0, then it implies that there exists no linear relationship between husband and wife's age. So in order to test that, the test statistic is given by r root over n minus 2 by 1 minus r square. So here, since this is a two sample thing, this is the same thing, so we'll just put it, and the value is 0.939 into root over, how many n's have they tested? 170. So it will be 170 minus 2 by root over 1 minus 0.939 whole square. And the decision rule, so the test statistic in this case is r root over n minus 2 by root over 1 minus r square, and the decision is we'll reject h naught rho equal to 0 if and only if rho equal to 0 against rho not equal to 0, if and only if the t observed, modulus of t observed is greater than a t distribution with n minus 2 degrees of freedom and alpha level of alpha by 2, because we are using modulus. So what it exactly means is that if this is t n minus 2 alpha by 2 minus t n minus 2 alpha by 2, then if the test statistics fall in this region or this region, then we are going to reject it. So in our case, what we have 0.939 into 1 root over 168 by root over 1 minus 0.939. So this one is how much? This one will come around 35.39. Okay, and T168 0.025, this will be this will be 1.97. Okay, so this one you can get the values from the table or some software. So here the rule, as per the rule, this is way more than what is the critical point. And so we are going to reject h naught and conclude that rho not equal to 0. So what I want to point out is that even though r is 0.939 based on our sample, rho might we are getting evidence that the actual population correlation is not equal to 0. Okay, based on some test, and this different from 0 is statistically significant. Is it okay? So if we are given even if we are not given the r value directly, we can calculate the r value using this formula, use this test statistic, and then get the revised test.
Ma'am, here in this in the test, R value is 0.939 whole square. Right?
No, R value is 0.939. Here it will be square. I'm sorry, here I forgot to put.
Yes, ma'am.
Yes. Thank you for pointing this out. Okay. So that is all I have for today. Any doubt? I think Mr. Kamal had some question.
Ma'am,
Yes.
um,
Oh, sorry, Miss
basic
Kamal.
question I have
Yes.
of previous assignment.
Okay.
Uh, can you tell me 10C3 is equal to 120? How?
10C3 equal to
Uh,
120.
yes.
Okay. 10C3 is 10 factorial by 3 factorial into 10 minus 3 factorial. So this will be 10 into 9 into 8 into 7 factorial by 3 factorial into 7 factorial. So this is getting cancelled. This 10 into 9 into 8 by 3 into 2 into 1. So this is 4, 3, then we have 120. What did you get, or what was it given?
I got something 15, sometime 30.
No. 10C3 you are saying, no?
Yes, yes.
10C3 is this one. Anything
Okay.
NCR is n factorial by r factorial into n minus r factorial. And
No, I was doing something like 10 into 9 upon 3 into 2.
no, that shortcut you cannot use, because this is 3 factor 3, no? That
Okay.
applies only when you have something C2. So
Okay,
this
okay.
will be n factorial by 2 factorial into n minus 2 factorial. This one you can write as n into n minus 1 into n minus 2 factorial by 2 factorial n minus 2 factorial. This one and this one gets cancelled, and this is n
Uh-huh.
into n minus 1 by 2 into 1. Okay. So this one,
Okay.
this shortcut will hold only if this denominator, I mean the NC2, but not for
Uh-huh.
something else. If it is 3 or 4 or something else, then it will not work. Again, but it will work if the difference is again 2. Okay. So 10C8 will again it work, because 10 factorial by 8 factorial into 2 factorial. Then it is 10 into 9 by 2. So if when only the difference is 2, at that time this shortcut will work, otherwise this will not work. Please be careful about this thing. Okay.
Okay, ma'am.
Okay, thank you so much. So
Thank you. Thank you.
any other question from today's session? If not, then I'll close. And if you do have questions, please post it in the discussion forum. Yes, Mr. Panju.
Yes, ma'am.
Hmm.
In the first problem we did, I had a question.
Today's first problem?
Yes.
Okay, I'll go. Ha, say.
So it shows like this observation is related to Poisson distribution or not.
Hmm.
Normally, like in binomial distribution, so we consider less than 30. Correct, ma'am?
Uh, yes, if we want to, no, see, if you want to fit a binomial distribution, you can also do it. What we are, so by, it's not a question of 30, it depends on types of distribution. So binomial, if you want to model number of successes in n independent trials, this will be a binomial distribution. Okay.
Yes.
Binomial np, out of n how many heads are you getting, if p is the probability of getting a head. So it's
Oh,
finite. It can, if x is binomial, it can take values from 0 to a certain point n. That is the total number of times you are tossing the coin. But here, for the number of defects, it can be infinite also. No, there is no upper bar to a number of defects in a book, like
yes,
ideally
ma'am. Yeah.
speaking. Okay.
Yes. Okay.
So that is why we are here trying to fit a Poisson distribution, because in cases when we are modeling some accidents or some rare events, because see, if in a publication or printing press the number of defects is actually it is expected that there will be less number of defects.
Yes.
So those sorts of rare events are usually modeled with a Poisson distribution.
Okay. Okay, ma'am. Thank you.
Okay, thank you. Anything else? Okay, then I'll stop today's session. Thank you for joining, and I'll see you next week. Thank you so much.
Okay, thank you, ma'am.
Thank you, ma'am.
Good night.